Hello and welcome to Lecture 18 for the course ECE 252B, Computer Arithmetic for Spring 2020. This lecture we start looking at Part 6 in the textbook, which has 4 chapters, as in other parts. Square rooting methods, chapter 21 is the subject of this lecture. Quadratic algorithms is the subject of the next lecture, which is the last one for the course this quarter. Now, I'm gonna be skipping chapters 23, variations in function evaluation, and chapter 24, arithmetic by table lookup, which is becoming increasingly important as we can afford to build larger and larger tables, given that memory cost has been going down substantially. So those are important topics, but within a quarter, there is no way we can cover everything. In fact, the entire Part 7 implementation topics is excluded from coverage in this course. If I get an opportunity, I may actually record lectures for these other chapters and just include them as additional information for reference, not required for this course. Okay, so Part 7, having chapters on high throughput arithmetic, basically pipelining, low power arithmetic, fault-tolerant arithmetic, and reconfigurable arithmetic, primarily doing arithmetic on building arithmetic circuits on FPGAs. So all 4 chapters in Part 7 will be ignored in this course, and chapters 23 and 24 also will be ignored. I could have combined some of the material in these 2 chapters in the quadratic lecture. Quadratic itself is quite important, and there are a lot of details to learn there, so it wouldn't have been a good idea to do that combining. As I mentioned, I may record lectures, chapters 23 and 24 later, and include them for reference for those who are interested. Okay, so square rooting methods is the subject of today's lecture. Now, whereas we could basically go straight to the computer version of multiplication and division algorithms, because everyone knows the pencil and paper or the manual algorithm, we cannot do the same for square rooting. It used to be that square rooting, manual square rooting, was taught in schools a long time ago. It no longer is, because people just don't have any use for the pencil and paper algorithm. So in this chapter, I basically start with the pencil. So I'll try to teach you the pencil and paper algorithm, because that's what we will use to build the computer algorithm. So notation-wise, we extract the square root of z, which we call the radicand. Remember, in division, we have dividend and divisor. We found the quotient. Here we have the radicand, the number whose square root is to be extracted. Z is a 2k-bit number, that's shown up here. The square root of z is a k-bit number, q. And there's a remainder in case z is not a perfect square, talking in terms of integers at this point. So if z is not perfect square, the square of an integer, then there will be a remainder, which is z minus q squared. Okay, this remainder, in fact, may have one extra bit compared to root. And the reason for that is that the remainder can be up to 2 times q. That's why we need an extra bit, because it's factor of 2. And why can it be up to 2 times q? That's the maximum. Because if it happens to be 2 times q plus 1, even one more than that, then z, which is equal to q squared plus the remainder, and if the remainder is 2 times q plus 1, this will be q plus 1 squared, so q is not the correct square root. I can subtract q plus 1 squared from z and still have a 0 or positive remainder. Therefore, q could not have been the correct square root. Therefore, the remainder can be up to twice. Remainder is always positive, but and from the other end, it can be up to twice q. That's why it has an extra bit. It's k plus 1 bits. So this is the dot notation representation of square rooting. So here I'm showing an 8-bit or 8-digit, doesn't matter. It can be in any radix. Radicand, the z. The square root of the radicand is this 4-bit or 4-digit root, q. And then the remainder s, as I mentioned, have one more bit or one more digit relative to q. So this 5 bits or 5 digits long. And I arrive at that final remainder by subtracting stuff from this radicand z. Very similar to division in a way. And the stuff that I'm subtracting are these values shown here. Now these will make more sense after I present the pencil and paper method and then justify essentially these. So for now, just let me just explain what this notation means without justifying it. So the first thing that I subtract, this thing up here, is Q3, the first digit, most significant digit, the quotient, times Q0, this is the zeroth partial root, which is empty at the beginning, 0 basically, attached with 0 Q3. So once I choose Q3, this will be 0 Q3. And I'm now describing this in binary square root. So for example, if this bit is 1, then this will be 0, 1. This bit is 0, this will be 0, 0. Then I subtract here, and then use the next 2 bits to determine or estimate what the next quotient digit will be. And subtract this value. Oh, by the way, I didn't explain this part. So this is the zeroth partial root attached. So this is attachment. It's not multiplication of these three things. Attach the zeroth partial root, which as I said is empty, with 0 with Q3. So that's why this will be 0 Q3, this number. In the next step, Q2 is multiplied by Q1, first partial root. So the first partial root is basically here. The first partial root is attached 0 Q2, which is the next digit here. And the result is multiplied by 2 to the 4. See, there's a 4-bit left shift. The first one had a 6-bit left shift. And then I do that subtraction, use the next 2 bits to estimate Q1, the next 2 bits plus whatever remainder I have here, partial remainder I have in these bits. Again, multiply Q1 by this number, which is the second partial root, the root up to here, attached with 0 Q1. Q1 is the next digit. And left shifted by 2 bits. 2 bits. And finally, the last quotient digit is determined by multiplying it. Once I've determined or estimated what Q0 is, I take the third partial root, which is this part of the root, attach to it 0 Q0, multiply this number by Q0. Multiply here is really easy because this is a binary digit. So it's either 1 times this, so it's basically this number, or it's 0 times this, which is 0, and no shifting in this last value. And then once I've subtracted all of these, what remains at the end is the final remainder of square root. Okay, as I said, I have not justified why I do this way. So let's now try to learn how we do manual square rooting and then convert the algorithm to its digital or computer version. Okay, so suppose I want to extract the square root of the decimal number 95,241. The square root of this number happens to be 308, because 308 squared plus the remainder, which happens to be 377, is 95,241, which is what we started. Notice that the remainder is larger than the root. As I mentioned before, it can be up to twice as large. Okay? All right. So how do I extract the square root of a decimal number using a manual algorithm? I first divide the number into groups of 2 digits from the right end. So first group, second group, third group, or you can say zeroth group, first group, second group. And then each group corresponds to a digit in the root. In other words, if I get 3 groups here, the root will have 3 digits. And this is easily provable. That a k-digit decimal number has a k over 2 digit root. Okay, so if k is odd, then it's k plus 1 over 2 digit root. So basically the number of groups, in this case I have 3 groups, 1, 2, 3, so I have 3 digits in the root. Final group can have single digits or 2 digits, doesn't matter, it's still 3-digit root. Okay, so now the first digit of the root is only a function of the digits of the radicand in this group. In other words, all the other digits do not affect the value of this first, the most significant digit of the root. In this case, because these 2 digits are 0, 9, basically, 0, 9, 3 is the correct root based only on this number 9. So I start with the first quotient digit, most significant quotient digit, being equal to 3. Okay, I square that and subtract. I get 0 remainder from this group. I use the next group, 5, 2. So now the second digit is a function of what I have here. It doesn't depend on these 2 digits. Okay, how do I determine what the next root digit should be, Q1? This is the procedure in the manual algorithm. I take the partial root up to this point, so I determine the first root digit to be 3. Partial root, which is basically the digits that I've determined so far, is 3. The zeroth partial root was 0. Okay? The first partial root is 3, first digit of the root. I double that partial root, give me 6, and then ask the question, what digit should I attach to the 6, Q1? What digit Q1 should I attach? So that's 60 plus Q1. So this is basically a 2-digit number. It's not 6 times Q1. 60 plus Q1 times Q1 is less than or equal to 52. 52 is the partial remainder here. So this is the key step in manual square rooting. I have to determine the largest value of Q1 that satisfies this inequality. So that's 60 plus Q1 times Q1 less than or equal to 52. It's easy to see that even 1 is too large choice for Q1 because 61 times 1 is 61. Does not satisfy this inequality, so the next quotient digit will be 0. The next partial root will be 30. Okay? I subtract 0 because this value is 0. I get 52. And then use the last group of digits for 1 to determine what the next root digit should be. Again, I ask the same question. Double partial root, 30 becomes 60. What digit should I attach to these two digits? Again, this is not 60 times Q0, it's 600 plus Q0. So 600 plus Q0 times Q0 must be less than or equal to 5241. It's easy to see that Q0 can be as large as 8. 8 is the largest value because we can verify that 9 is too large. 609 times 9 will be greater than 5241. 608 times 8 is less than or equal to 5241. So the next root digit is 8. Partial root, or the final root in this case, is 308. And subtract, so this is basically 608 times 8, which is 1,864. So I subtract, get 377 for the remainder. So this is the manual square rooting algorithm that I was taught in school. Nowadays it's not taught in school. Because we basically don't have a need to do manual square root extraction with calculators and computers being so readily available. Okay. We can view square rooting as division with an unknown divisor. So in division, we have the dividend, and we have a divisor here, and then we develop the quotient here. In this case, I'm dividing this number by square root, and quotient will also be square root. Okay, so you can view it in this way. This divisor is not known. As I develop the first digit of the square root, I also get to know the first digit of the divisor. Okay, so I multiply Q3 by Q3 and subtract the result. And then now I have to determine Q2 based on what I see here. As I mentioned when discussing the previous slide, Q3 depends only on Z7, Z6, the digits or bits in the last group, most significant group. And here's a simple justification. I won't go through it. You can read. It's not that hard to understand. Basically says that no matter how large these digits are, their value is not enough to increase this first digit even by 1. So epsilon is by how much these digits can increase the first digit of the square root. And we see that even if epsilon is equal to 1, it doesn't work in this equation. Okay. So this process continues. I determine Q2. And I determine Q1. And finally, I determine Q0 and then get the remainder at the end. Again, so the reason that the manual square rooting algorithm works is that the first digit of the root is only dependent on these 2 digits. The second digit of the root is only dependent on these 4 digits, and so on. So why is it that I use that inequality to guide me through the selection of the root digit? Here's an explanation. So in step I, I've already computed I digits of the square root. Let's say I'm doing decimal square rooting. So first digit, second digit, ith digit. And I'm now working on determining the I plus first digit of the square root. Attaching this I plus first digit to the partial root will make the next partial root 10 times the previous partial root plus the new digit. Basically, when you attach a digit to the right end of this, you're forming a number that is 10 times whatever number this is, plus this digit. Okay, so this will be the next partial root. Okay, so in this algorithm, I always aim to subtract the square of the partial root from the initial value, the radicand. So after the next step, I need to compute subtract from the radicand the square of this number. What is the square of this number? So square this 2-term expression. Get 100 qi squared, the square of this term, plus qk minus I minus 1 squared, the square of the second term, plus 2 times the product of these two, 20 times qi times qk minus I minus 1. So this is the value that I need to subtract from the partial remainder once I've determined what the next root digit will be. Of these values, I've already subtracted in previous steps this value. Okay, I really subtracted qi squared, then because now qi has been made 10 times more important by the addition of this value, I really subtracted 100 qi squared. So that part has already been subtracted. I need to subtract this amount in the current step. That amount I can write in this form. 10 times 2 times qi times qk minus I minus 1. So that's that part. Plus qk minus I minus 1 squared. So basically, of these two terms, I factor out qk minus I minus 1. From this, I'm left with 20 qi, 20 times the partial root to this point. And I write that as 10 times 2 qi. Okay, so basically, this is the justification for what I said before. You double the partial root up to this point, and then attach a digit to it. So this is basically a number that is formed by attaching this new digit to twice the partial root up to this one. Okay, and then multiply by qk minus I minus 1. So to make sure we understand this, let me go back to that slide where we did. Okay, so here it is. Double the partial root 6, attach a digit to it such that 60 plus q1 times q1 is less than or equal to 52. Okay, we try to keep the remainder positive, therefore we do not want to exceed this partial remainder. Okay, alternatively, we make the wrong choice here. Once we do the subtraction and the partial remainder goes negative, we realize that this quotient digit that we chose was too large. We reduce it. And in binary, actually, the process is very simple because Q1 is either 1 or 0. So basically, I attach 1. I say, okay, let's try 1. I attach 1, and I get this number, and I subtract it. It's called the trial subtraction, like we had in division. And if the result of the trial subtraction goes negative, 1 was too large, which means that 0 is the correct quotient digit. If the result remains positive, then 1 is the correct quotient digit. Okay? So in binary, we have just one trial subtraction. In decimal, actually, we may make a mistake. Let's say the quotient digit is 6. We may think it's 7. We try 7. We see that it's too large because the remainder goes negative. And then backtrack and use 6. Maybe even 5. If we are not very skilled in doing these estimations, we may actually estimate the quotient digit value that is too large. Okay. So this is why that rule works. Double the partial root up to this point. Attach a digit to it so that this number, the attached digit, times the value of that attached digit is no greater than the partial remainder. Okay, more generally in radix R, so this was the radix 10 algorithm. In radix R, this is what we do. Double the partial root, attach a radix R digit to it, so this is the number we get, then multiply by that chosen radix R digit, and ensure that this value is not greater than the partial remainder. So in radix 2, our radix R is 2, so here I have 2 times 2qi, 4qi, plus qk minus I minus 1 times qk minus I minus 1. So this is, if the quotient digit is 1, then 4qi plus 1 times 1. Okay, times 1 you can ignore. So 4qi plus 1 is basically qi attached with 0, 1 at the end. Okay, 4 times qi is basically qi followed by 0, 0. That's 4 times. And then plus 1 is this. So basically, the value that I subtract in my trial subtraction consists of the partial root appended with 0, 1. And then if the result of that trial subtraction is positive, I simply choose quotient digit 1 and continue. If the result goes negative, I restore the partial remainder to its original value and choose 0 as the root digit. Okay, occasionally I may speak of quotient digit. I apologize for that. The notation is the same as in division, which we use Q for quotient digit. Here we are using Q for root digit, so I may misspeak at times and call it quotient digit. It's really root digit in the context of this chapter. Okay, so let's do a binary square root using the manual algorithm now that we know how it works. So this 8 number has a 4-bit square root. Remember, groups of 2 digits, and there are 4 groups, so there are 4 root digits, or root bits in this case. First part, the 0th partial root is 0. I attach that with 0, 1. So this is my trial subtraction. Okay, is this partial remainder greater than or equal to 0, 1, which was formed by appending 0, 1 to the end of the partial root? The answer is yes, or the trial subtraction yields a non-negative result, and therefore the first quotient bit is equal to 1. Then my partial root at this point is 1. I append 0, 1 to the end of it, and I ask the question, is this partial remainder greater than or equal to 1, 0, 1? It is not. Okay, so the next quotient bit is 0. I subtract 0, or just use this remainder for the next step. And then use the next 2 bits, 0, 1. And then again, 1, 0 is the partial root. 1, 0, appended with 0, 1. Ask the question, is 1, 1, 0, 1 greater than or equal to 1, 0, 0, 1? The answer is yes, so the next question is 1. And finally, in the last step, I now have 1, 0, 1 as the partial root. Appended 0, 1. Ask the question, is 1, 0, 0, 1, 0 greater than or equal to 1, 0, 1, 0, 1? It is not. So the last quotient is 0. I subtract 0, and this is my remainder. So basically 118, which is the number I started with, is equal to 10 squared plus 18, remainder of 18. So 10 is this number, 1010. 18 is this number, 16 plus 2. And again, notice that the remainder is larger than the quotient. It can be as much as twice as large. Okay. Now we understand the manual square rooting algorithm. We just have to implement this in hardware. Now, as in division, these variable shifts that you see here, this is a 6-bit shift, this is a 4-bit shift, this is a 2-bit shift. So these alignments are inconvenient, but we notice that each value relative to the previous one, so this 0, 1 compared to this 0, 0, 0 compared to 1, 0, 0, 1, is right shifted by 1 bit, okay? Looking at it from the left edge of the number. Therefore, instead of right shifting the next value by 1 bit, I can left shift the previous result, the partial remainder, to the left by 1 bit for proper alignment with the next value to be subtracted. This is also seen in this dot notation. You see each value. This one is aligned with the left end of the number. This is right shifted by 1 bit, right shifted by 2 bits. So let us formulate now square rooting algorithm, the recurrence, similar to the one we had for division in terms of the IEEE standard, because square rooting is primarily done for floating point numbers. We seldom extract the square root of integers or fixed point numbers. Although we can do it once we understand the algorithm. But the primary use of square rooting is on floating point numbers. So let's take IEEE floating point number. Normally its significand is in the range 1 to 2. The number whose square root we extract can be in the range 1 to 4, because in the case of an odd exponent, you reduce the exponent by 1 to make it even, and left shift the significand, thus doubling it. So the number that we are left to extract the square root of is in the range 1 to 4, and the exponent is either even to begin with, or we made it even by incrementing it by 1. So we just divide the exponent by 2 and extract the square root of a number in this range. Now the square root of a number in this range will be in the range 1 to 2. So we get directly the value for the significand of the square root that is in the proper range. We don't need any adjustments after the algorithm is executed. So the radicand is in the range 1 to 4, which means it has 2 whole bits and let's say L fractional bits. L will differ depending on whether we are using the short format or the long format. The square root is always of the form 1 point is in this range, and then L fractional digits. And the remainder can be twice as large, so it has 2 whole bits. Okay, now the first bit of the square root is always 1, and then normally we have to square that and subtract it from. So we might as well just skip that step and initialize our partial remainder to z minus 1. In other words, subtract the square of 1, and then focus on determining the rest of the bits in the quotient. So initialize the partial remainder to z minus 1. And z minus 1 is easily computed because you'd simply take the whole part, which is in the range 1 to 4, and subtract 1 from it. So it's basically a simple computation depending on these 2 bits. Okay? And Q0 is already 1, already determined before even entering this recurrence. And the remainder, the jth remainder will be the final remainder. And this is the recurrence. Double the previous partial remainder and subtract from it this value. And this value, basically, as I mentioned, is the jth partial root appended with 0, 1. Negative trial difference means that the next quotient digit should be 0. A positive trial difference means that the quotient digit is 1. Okay, so if you notice, the recurrence is very similar to division. In division 2, we had the left shift of the partial remainder and then subtraction of something. And that something basically was the divisor in the case of division. Here it's a bit more complicated. What we subtract is this number that is formed by the partial root appended with 0, 1. Okay, so let's do a numerical example to make sure we understand this algorithm. The radicand is this number. It has 2 whole bits and 6 fractional bits. Okay. And then the algorithm says left shift. Oh, so that the zeroth partial remainder is z minus 1. Z minus 1 basically removes this one. Okay? So it's same as z with this 1 removed. And then 2s0, shift left. And subtract from it 2 times. The partial root at this point is 1.0 because that digit 1 already predetermined. So 1.0 multiplied by 2, or attached with 0, 1, okay, and then multiplied by 2. So I do the subtraction, and notice that the result goes negative. I've added this extra position to keep track of the sign of the values. So the sign bit is 1, therefore the result went negative, which was predictable because you see here, this is 1 point something, this is 2 point something. Okay, result went negative. Restore the partial remainder to S0, which was up here. Then left shift, repeat the process. Each time you left shift the partial remainder and do the trial subtraction, the term you're subtracting, the number you're subtracting, is formed according to this expression that you see here. Okay, you can use this one. So basically, q minus j1, that's what you're trying to determine. Is it 1? So q minus j1 cancels this term. This one is removed. So it's basically 2 times qi minus 1 plus 2 to the minus j. Okay? So this is what we have. 2 times previous partial root plus 2 to the minus j. So 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4, and so on. And each time, the first term is twice the previous partial root. Okay, I will let you examine the rest of the steps so that once you know what you're trying to do, it's pretty mechanical from this point on. So each time you left shift the partial remainder, subtract value given by this formula, which is twice the partial root plus 2 to the minus j. And then if the result is positive, as is the case in this step, keep that, double, and proceed. And the quotient digit is 1. Whenever the result goes negative, as this step or this step, choose the root digit to be 0 and restore the partial remainder to its previous value. So you discard the result of trial subtraction. Okay? Now, the thing is, in square rooting, we are usually not interested in the remainder, except as something to use for rounding the value. In other words, if the remainder is large, then rounding up the root makes it closer to the correct root value. Okay, if the remainder is small, so basically the rule for rounding is this: you develop one extra bit or one extra digit in other radiuses of the root. In other words, here if I continued the digit q minus 7, which is basically, this is my q minus 7, the next here will be 1. Because it's 1, I round up. If it turned out to be 0, I would just discard it, truncate, okay? So just one extra digit of the root will allow me to properly round the root something that is as close as possible to the exact root. Okay, so a natural question at this point is, I understand that when this is 0, that means the value of the additional bits, if I went ahead and developed more bits, would be less than 1/2 ULP. Therefore, we just chop them. If this is 1, then perhaps all the remaining bits be zeros. Okay? And then that's the midway point. Remember, we talked about rounding in IEEE floating point standard. When you are at the midway point, you round to even. In other words, if you have a 1 here, everything else is 0, you round to even. In other words, this digit is kept at 0, you essentially discard the 1. If this bit were 1, and you had a 1 here, then you round up. Okay, the question is, why do I develop just 1 bit and do not proceed further to see whether every other digit after this is 0? And the answer is, it's provable that those digits, those bits, cannot be all zeros. It's impossible. So it's an interesting exercise in math to prove that. So if this bit is 1, over here, the 7th bit in this example, then it's guaranteed that there's at least some other non-zero bit further on. So this is result is greater than 1/2 ULP, and therefore I round up. Okay? So the midway point provably never occurs, which is relief because we can just develop 1 extra bit, 1 extra digit, and properly round the result. So this is a hardware square rooter based on what I just described. It's very similar in terms of the components and their arrangement to a divider. Okay, so this is where we put the radicand at the beginning, and it will hold the partial remainder throughout the process. I do the trial subtraction, okay, which is basically the partial root ended with that 0, 1 that I mentioned. So this adder has to be wider than the fractional part of my number by 2 bits because that left shifting is required. So I do the trial subtraction, and then the sign of this trial subtraction, as well as this bit that was shifted. So if this bit is 1, just like division, then partial remainder is larger than the number I'm subtracting from it. If that bit is 0, then I look at this carry out. So these 2 bits are needed for me to select the quotient digit. Quotient digit is 0 or 1. In either case, the digit is shifted. But q minus 1 is determined first. Q minus 2 is determined second, so they're shifted in, and they move left with each step. Okay? And then if q minus j is equal to 1, if I decide that trial subtraction result was positive, therefore I choose 1, then and only then I load the result of the trial subtraction into this register. If this digit is 0, if this bit is 0, then I don't load. This signal will not be asserted, and the old partial remainder is kept there. So really, I'm not doing any restoring. I just don't change it in that case from its correct value. Okay, and I do subtraction, the trial subtraction, by complementing the partial root and also inserting a carry in. This is standard use complement subtraction. Right? So compare this to a divider circuit. You see that the components are very similar. And in fact, we can use the same hardware with the control unit basically deciding how to use the hardware. I can have one piece of hardware that does multiplication, division, and square rooting, depending on my choice. Control unit simply manages the steps differently for the three operations. We are using the same components in terms of registers, the adder required. In this case, the adder should be wider, but I can build the adder wider, even though the wider adder is not needed here. Okay, I already talked about rounding the square root. I developed an extra bit or extra digit in higher radiuses. In the midway case, where the extra digit is 1 followed by all zeros, is impossible. And this is the subject of problem 21.11 at the end of the chapter. Okay, now in division we had restoring and non-restoring algorithms. We also have a non-restoring square rooting algorithm that basically when we do the trial subtraction, instead of restoring the remainder to the correct value, we keep the incorrect value, which is negative, and then remember to do addition in the next step. The details are a little bit different from division in this case. So this is basically subtract, storing, square rooting. If we have to add, it's provable, and I'm not going to prove it here, that we have to add this value in the next step. So we subtract this if the partial remainder is positive. We add this if the partial remainder goes negative. So the thing that is subtracted and the thing that is added are different. Unlike in division, where the same thing would be subtracted or added depending on the sign of the partial remainder. Okay? Not only these two are different, this number is not easy to form. Remember here, this number is basically appending a 1 at position minus j. So when I shift this to the left by 1 bit, position minus j is guaranteed to be 0. It's empty. So adding to the minus j is simply changing that 0 to 1. So it doesn't involve any arithmetic operations. It's just basically adding a 1 at that particular position. This one, however, cannot be formed in the same easy manner because you're subtracting to the minus j. You're not adding. Adding would be insert a 1 in that position. Subtracting 1 from that position may result in carries, and therefore formation of this number is not trivial. Okay? I'll show you in a minute how you get around this problem. Okay, but for now, ignoring that, let's look at the numerical example. So the things that we are adding are, or subtracting is the same thing as we did before, or in case the partial remainder goes negative, we add a similar term except there's a minus here, okay? So suppose I somehow magically compute that value. So 2 times 1.1 minus to the minus 2. Okay, so 2 times 1.1 is 11.0. 11.0. So 11.00. When I subtract 1 from here, borrows propagate, turn the number into this. Okay, so I'm not going to worry at this point how I form this number. Assuming that I form it, then the process works, and I get the binary quotient. Just as in non-restoring division, if the final remainder is positive, then we are okay. And in this case, the final remainder happens to be negative, so I need a correction step to turn the final remainder into a positive value. And that correction basically subtracts ULP from the quotient. So this is the uncorrected quotient corresponding to this negative remainder. This is the corrected quotient corresponding to the corrected positive remainder. Okay, so very similar to non-restoring division, the exception that the terms that we add when addition is required due to the partial remainder going negative are different, okay, how they are formed. Okay, so depending on the sign of the partial remainder, we add one of these two values. Subtract or add. We subtract in case the partial remainder was positive. We add if it's negative. So remember that number 2qj minus 1 plus 2 to the minus j is formed by concatenating 0, 1 to the end of qj minus 1. This other number cannot be formed by concatenation, but here is what we can do. We keep the quotient so far in two forms, the regular quotient, which we call q, and the diminished quotient, which we call q star. So the diminished quotient is always 1 ULP less than q. So if q ends in 1, q star ends in 0, okay, 1 ULP less. If q ends in 0, then this will be 1 less than that. So for example, if it ends in 1, 0, q star, so this is basically q, I subtract 1, q star will end in 0, 1. Okay? And then as I proceed through the division algorithm, whenever I choose the quotient digit to be 1, I update the partial quotient. Okay, so the new partial quotient becomes q1, appended with 1. I decided the quotient digit to be 1, so I append q with 1. Q star, which is the diminished quotient, will be q followed by 0. So there are two registers in which I keep the real quotient and the diminished quotient. Every time I decide on the quotient digit, if I decide it to be 1, I update this register by appending it with 1. I update the second register by appending the contents of the Q register with 0. So I transfer the contents of Q register to this register and put the 0 at the end. If I decide that the quotient digit should be -1, then Q will be updated by putting the value from Q star, appended with 1. Remember, this is 1 unit less up to this point. So instead of subtracting 1 from Q, I add 1 to Q star, okay? And the new Q star will be Q star 0, 1 unit, 1 ULP less than this. And now if I decide to use 0 as also as a valid quotient digit as we did in SRT division, then I can extend these rules. If I decide the quotient digit should be 0, the partial root is updated by appending it with 0, and the diminished root is updated by appending it with 1. So with this trick of using two registers to hold Q and Q star, I can form both of these numbers equally easily without doing arithmetic. by just appending bits. So in this case, I append 1 at the end of the quotient. In this case, I append the 1 to the end of the diminished quotient, which is in a different register. Okay. So this is non-restoring square root. We can also do high radix square rooting, similar to division. The idea being that instead of developing the root bits in binary one at a time, we can develop them two at a time doing radix 4. So in the first step, I determine what these 2 bits should be, or the corresponding radix 4 digit. And in the second, I determine what these 2 should be. So I need only 2 steps, 2 subtraction. Now, of course, if I determine that these 2 bits should be 1, 1, 3, I have to multiply 3. Okay, so this quotient digit is now 3, and it's not as easy to form this term that is to be subtracted. So we use tricks similar to what we had for division. For example, we can do radix 4 square rooting, digits ranging from -2 to 2. Okay, so here is an algorithm. I just show it to you without justifying the details. So whenever I choose the quotient digit to be 2, I have to subtract this value, and that value is obtained by appending the Q, contents of the Q register 0, 1, 0. If I choose it to be 1, then I need to do this. I need to subtract this. And so this is what I will be subtracting. Okay, similarly for the other ones, again, I can add 0 as an option for the root digit, and that has its own rule for forming the new partial root and the new diminished partial root. Okay, as in division, we may think of keeping the partial remainder in carry safe form, because if we do this, we don't have to do a full carry propagate addition or subtraction in each step. Steps can go faster, and we can do that addition or subtraction, real addition or subtraction in the final step. Okay? This complicates the result because now we have to estimate the root digit based on 2 numbers. Okay, carry safe partial remainder has 2 components. As in division, we do an approximate estimation by looking at a few bits of the 2 components. Okay, but the process is a little bit more complicated here because there's more uncertainty as we are developing the root. Remember, the root is also the divisor, using the division analogy. So in division, we did have the divisor. We have the full divisor in front of us that we can use in estimating the next quotient digit. Whereas as we are developing the root, the digits of the divisor also emerge one at a time, and therefore we have less information about the divisor, especially at the beginning where we have not yet developed any digits. Okay, so it's a little bit more complicated. This is all I want you to know. We can do it, and the details are provided in some of the end of chapter references. Okay, this brings us to, just as we did division by convergence, we can do square rooting convergence. So square root of z is a solution to this equation, x squared minus z equal to 0. I equate x squared minus z to 0, solution of that equation is x equals square root of z. Okay? So this is the function x squared minus z. So if x is 0, we get minus z. x0 gives us minus z. At square root of z, curve intersects the x-axis, that's the root, and then it goes up. So I can use the Newton-Raphson method, and I leave it up to you to derive the details. Now that you know that method, you have to find f prime, and then substitute here, and we get this recurrence. Start with an initial estimate for the square root, x0, and then refine that estimate by using this formula. Okay, so the formula says the previous estimate plus z divided by the previous estimate. So I need one division, one addition, and a right shift times 0.5. So each iteration involves one division, one addition, and a right shift. And then I converge to the square root quadratically, like the division or reciprocation algorithm that we discussed. This also has quadratic convergence. So if z, let's say in the range 0.5 to 1, a good starting approximation for x0 is 1 plus z over 2. If z is 0, z is 1, the upper range, this will be 1, which is an exact value for the square root. If x is 0.5, if z is 0.5, the lower range, this is 1.5 divided by 2, which is 0.75, okay, which is pretty good approximation. And notice that forming this value does not require any computation. Z is a fraction, it's less than 1. So adding 1 to it is basically putting a 1 in front of it. And then divide by 2 is right shift. The error is 0 at z equal to 1. There's a maximum of 6.07% at z equal to 0.5. So we start with an error in the initial approximation, no greater than about 6%. And then quadratically, we converge to correct square root. So notice that 6% is less than 0.1. Okay. So this is in decimal arithmetic already accurate to 1 decimal digit. And the first iteration gives us 2 decimal digits, and 4 decimal digits, then 8 and 16. So very quickly it converges to an accurate square root value. Okay. I'm skipping some stuff that are not all that important, focusing on the basics. Okay, we can use table lookup to find a better starting approximation, just as we did for division. So we look at a few leading bits of z, and let's say we have a fairly large table that gives us the square root an accuracy of 8 bits. In other words, the error is no greater than to the minus 8. So we have 8-bit accuracy to begin with. The first iteration gives us 16-bit accuracy, and 32-bit and 64-bit. So we need very few iterations to get a 64-bit square root. So here's a numerical example. I want to extract the square root of 2.4. And from a table, I read out the approximate square root of 2.4 is 1.5. And the table guarantees an accuracy to within 10 to the minus 1. Iterate once, 10 to the minus 2. Iterate the second time, 10 to the minus 4. Iterate the third time, 10 to the minus 8. So this square root value is accurate to 8 decimal digits up to here. And I can check, raise this value to the power 2, square that, and sure enough, you get something very close to what we started. Okay, now, because division is a slow operation, we have discussed this before, people have been looking for iterative methods for square rooting that does not involve division. So we typically have fast multipliers, almost all computers, and we have fast multipliers on FPGAs. So we prefer to use multiplication rather than division here in order to avoid the complex and slow division operation. So this slide basically describes two methods that have become obsolete because of a better method that comes the next slide. So these methods are known as division-free convergence square rooting. The convergence method. Oh, sorry. This is an example for the previous slide. So let me go here. So this is preferred method nowadays. It's actually based on computing not square root of z, but 1 over square root of z. But once I have 1 over square root of z, I can simply multiply it by z to get square root of z. So I need one extra multiplication at the end if I compute instead of square root of z, 1 over square root of z. Okay? And it turns out that the function for this is pretty convenient. It leads to a convergence method that does not involve division. So this function, f of x, has a root at x equal to 1 over square root of z. Okay, you can verify by computing the f prime and plug it into the Newton-Raphson iteration formula, and you get this. So from a previous approximation to the square root, find the next approximation by doing a squaring here, say 1 multiplication, 2 multiplications, an addition, third multiplication, and a right shift. So each iteration involves 3 multiplications and 1 addition. And shift we can basically discount because it's a very simple operation. Okay, so we are avoiding division. The method still has quadratic convergence. So here is a numerical example. Suppose I want to extract the square root of 0.5678. I read out from a table the approximate inverse square root of this number is 1.3. So remember, the convergence method computes 1 over square root. The inverse square root of this number is approximately 1.3. Plug into the equation, I get this. Plug it again, I get this. And this is already accurate enough. And I just multiply that final result for 1 over square root of z is z to get square root of z. A Cray 2 supercomputer implemented this method basically popularized this method and also had an ingenious method to reducing the number of iterations this way. Initially, instead of x0, the two values 1.5 x0 and 0.5 x0 cube I read out from a table. So in this formula, what we have is 1.5 x0. Okay, so given z, given a few bits of z, we read out from a table directly 1.5 x0 and 0.5 x0 cube. 0.5 x0 times x0 squared. So once we have those two numbers, 1.5 x0 and 0.5 x0 cube, I just need one multiplication and one addition. Okay, so addition is typically faster, so that's why it says just one multiplication. The value x1 obtained from this table lookup and one multiplication and one addition is already accurate to within half of the machine precision. So they use large tables, fairly large tables, so that this is already accurate to within. Cray used 60 bits floating point arithmetic. So this is already accurate to within 30 bits. And then I just need one more iteration, which involves 3 multiplication and an addition. So total, we have, and then of course the one multiplication at the very end. So I have 3 multiplications here, 1 multiplication here, 1 multiplication there. Total of 5 multiplications, 2 additions, and 2 shifts. To compute an accurate square root value, which is pretty impressive. Only 5 multiplications. And division is completely avoided. Okay, so for this scheme to work, we need either a table lookup, and an analysis similar to what we did for division can be done for square rooting to find the size of the lookup table required to achieve a certain amount of convergence after the first step. Okay. There are also fast hardware square rooters that give you a reasonable estimate with very little investment in hardware. They're quite fast and energy efficient too. So this is the function square root of z plotted between 1 and 4, which is the range we need for IEEE floating point arithmetic. So this is the function we are trying to approximate. Okay, I'm going to show you successively better approximations. 1.5 is an approximation that does not require us to do anything. It's always a constant. That green dashed line is that approximation. And you see that the error is 0.5 at the lower end of the range and 0.5 at the upper end. So this error is 2 to the minus 1. So even this very primitive approximation has an error 2 to the minus 1. So if you iterate, it becomes 2 to the minus 2 in the next step, 2 to the minus 4, 2 to the minus 8, 2 to the minus 16. So you need a few iterations, but the accuracy doubles in each step. Okay, we can do a lot better than that. So here is an example. Blue line, blue dashed line, is the approximation 1 plus z over 4. Now z being in the range 1 to 4, z over 4 is a fraction. Okay? And therefore adding 1 to it is simply sticking a 1 in front of it. Z over 4 is basically a 2-bit right shift. So 2-bit right shift of z, and then sticking a 1 in front of it gives you this approximation, which is better. It has no error at the upper end, and the error is pretty small. Okay, it's 1/4, 0.25 at the lower end. It's 2 to the minus 2. Okay, so if you use this approximation, you avoid one of the iterations because you start with 2 to the minus 2 instead of 2 to the minus 1. Again, we can do better. This is red dashed line, a better approximation. Notice that the error is cut in half again, the lower end, but we also have error in the upper end. That's also the same magnitude as this. So the maximum error is now 1/8 or 2 to the minus 3. Okay. Now, however, this cannot be computed as easily as that one. Z over 4 is still a fraction. 7/8 is also a fraction. You need an actual addition to compute this. So you need one addition step to compute this approximation. This is the best linear approximation, the purple line. It again cuts the error at both ends. Now this one involves division by 3 and an addition. If you remember, division by 3 is a division by constant, so you can do it through several simple shifts and adds, and then an addition. Okay? So you do invest a little bit upfront to find this approximation, but then you get a much smaller error and therefore faster convergence. And of course, we can also, so here we are basically approximating Z, the linear function, different linear functions with different error characteristics. We can also approximate Z not with a single linear function, but with multiple linear functions in different subranges. And this is very easy to implement using table lookup. So for subrange 1 in the range 1 to 2, we may use a different linear approximation than for the range 2 to 4, therefore cutting the error even further. The subrange is basically very easily determined. The number is in the range 1 to 2 if it begins with 0, 1. The whole part is 0, 1. In the range 2 to 4 if it begins with 1. Okay, so by just looking at the two leading bits, we know which subrange we are at, and we can solve the appropriate table or use the appropriate circuit to do two different interpolations depending on subrange. So for example, I can do, even without tables, I can do the approximation 1 plus z minus 1 over 2 for subrange 1, and 1 plus z over 4 for subrange 2. Again, 1 plus z over 4 involves no computation. Okay, but it's a better approximation. This one, I used 1 plus z over 4 for the entire range. That's why the error was rather large. If I use this approximation only for this range 2 to 4, okay, the error is better. So the blue line only from here to there. And then this one, if z is in the range 1 to 2, z minus 1 is just dropping the whole bit. Dividing by 2 is shift, and then this is basically putting a whole bit in front of it. So drop the whole bit, shift to the right, and insert a whole bit in front of it, so it's still easy to compute. Okay, so there are a lot of different ways to approximate square root. Either just as a way of computing square root when high precision is not required. So in certain signal processing applications, these approximations may be good enough, but they certainly can be used as the starting approximation for convergence methods. Okay, we also have array square rooters. This array square rooter is based on non-restoring algorithm. And the cells that you see here are basically control adder subtractor cells. So if this signal is 1, we do subtraction, we complement that. If this signal is 0, we do addition. And that signal comes from the root digit. If root digit is 1, meaning the partial remainder did not go negative, therefore means do subtraction in the next step as well. This root digit is 0, means the partial remainder went negative, so we do addition the next step. Okay, so this is enough for us to know about array square rooters. And so basically, you see here partial root appended with a couple of digits there is being used as the trial subtractor. Okay, and there's also a numerical example here that shows what happens for a particular radicand, which comes in from the top, and the root, which is developed at the left, 1010. Okay, this is verification that this was the correct division result. Doing the division square rooting, according to the method that we saw at the beginning of the lecture. Just, confirmation testing. And I mentioned already the square root is not a special case of division. When you have a multiplier, both inputs connected to x, you get a squarer. We saw that a squarer actually can have a simpler design than a multiplier. So we usually do not use a multiplier to form the square of x, unless the multiplier is already there and we don't want to add another piece of hardware for squaring. In many special purpose hardware units, actually develop a squaring circuit because squaring can be faster, less complex in terms of hardware, and more energy efficient. Okay. However, square rooting is not easier, less complex, or more energy efficient than division, because square rooting is not a special case of division. In fact, the square rooting algorithm is slightly more complex than division. Okay? All right, that's all I wanted to say in this next to the last lecture for our course. I will record the final lecture pretty soon and post both of these to the course webpage, and then we'll be done with the basically lecture part of the course. We still have one more homework left that I will post by the end of this week. And of course, we have the research paper that you're working on as the second component besides homeworks for determining your grade. I'm looking forward to reading your research papers after you submit. Okay, take care, stay healthy, and I'll see you in the next lecture.